This microscopic evidence of explosive effects from mass defect in spent nuclear fuel. Overview. Microscopic analysis of spent nuclear fuel reveals compelling physical signatures that suggest nuclear reactions, where mass defect occurs, are accompanied by highly energetic, explosion-like processes at a microscopic scale. These observations challenge the standard idea that mass defect merely translates into emitted energy, proposing instead that the defect produces an extremely powerful microscopic explosion within the material. Key observations from microscopy. 1. Spherical and quasi-spherical damage zones. Findings. High-resolution electron microscopy of irradiated nuclear materials frequently reveals distinct spherical or quasi-spherical regions of damage around fission sites. Implication. These zones resemble the effect of a miniature explosion or blast radiating outward from a single point, much like the damage one would see from a shockwave passing through a solid medium. 2. Radial microcracks. Findings. Fine, radial microcracks emanate from the core of these damaged areas. The pattern points to intense local pressure spikes, sufficient to fracture even robust crystalline lattices. Implication. Such microcrack networks are analogous to those generated by sudden, violent decompression and pressure release, again mimicking classic explosion effects. 3. Amorphous and melted regions. Findings. Zones neighboring fission sites often display evidence of rapid heating, melting, and subsequent solidification. Crystal lattices in these regions become disordered or amorphous, indicating extreme thermal and mechanical disturbance. Implication. This level of localized heat and melting is difficult to explain purely by radiation damage, supporting the idea of a brief but exceedingly powerful energy release, essentially a microexplosion. 4. Shockwave signatures. Findings. There are observable shockwave patterns in the microstructure, such as concentric rings of deformation and regions where material appears compacted or densified due to pressure waves. Implication. These microstructural features are direct physical evidence for the propagation of a mechanical shock, which aligns with the effects caused by a small-scale, explosive event. Mechanism. Linking mass defect to microexplosion. Nuclear reactions, like fission or fusion, produce mass defects. Some mass disappears compared to the sum of reactants and products. Instead of simply converting to energy, the theory proposes this mass reappears as tiny, energetic particles or a fine form of matter. The sudden emergence and expansion of this new matter within the crystal lattice would produce an intense pressure pulse. This pulse radiates outward as a shockwave, fracturing and deforming the surrounding material, exactly as observed microscopically. This conversion constitutes a microscopic explosion, leaving permanent physical markers in the fuel structure. Why traditional explanations fall short? Standard models attribute damage solely to kinetic energy of fission fragments and radiation. However, the blast-like damage patterns observed, such as spherical zones, radial microcracks, and minute shockwave evidence, are more consistent with an explosive pressure change than with thermal or radiative effects alone. The unique combination of heat, pressure, and rapid expansion observed at these sites suggests a fundamentally explosive phenomenon rooted in the release and transformation of the mass defect. Conclusion. Microscopic analysis of spent nuclear fuel uncovers a variety of physical and structural anomalies, spherical damage zones, radial cracks, amorphization, and shockwave signatures, that together present strong evidence for a powerful, explosion-like process tied to the mass defect. These findings point to the mass defect producing not just energy, but a genuine microscopic explosion capable of modifying material at the atomic level. This challenges conventional interpretations of nuclear reactions and supports the idea that the mass defect has physical, explosive consequences that can be directly observed in irradiated materials. The exploding mass defect. Microscopic evidence rewriting modern physics. Overview. The exploding mass defect. Microscopic evidence rewriting modern physics is a groundbreaking work that challenges long-standing assumptions in nuclear physics and cosmology. The book examines how the phenomenon of the mass defect, traditionally explained as a conversion of mass directly into energy, as per Einstein's equals mc², may in fact conceal a more profound process occurring at the heart of nuclear reactions. Through a blend of experimental observations and innovative theoretical perspectives, the author proposes a radical reinterpretation of how mass, energy, and matter interact in both the microcosm of the atomic nucleus and the larger structure of the universe. Core thesis. The key argument of the book is that the missing mass defect, observed in nuclear reactions does not simply vanish as energy. Instead, it explosively transforms into an extremely fine, previously undetected form of matter that permeates space. This form of matter, sometimes likened to a rejuvenated concept of the ether, is hypothesized to be responsible for propelling nuclear reaction products, much like the blast wave in a chemical explosion, playing an active role in phenomena traditionally explained by relativity and quantum mechanics. Main concepts. 1. Rethinking mass energy equivalence. The book disputes the direct conversion of mass into energy, suggesting that the mass defect initiates a phase change, turning into fine matter rather than pure energy. Nuclear reactions, whether fission or fusion, are described as microscopic explosions that generate space-filling fine matter. This reinterpreted process redefines how energy is imparted to nuclear fragments. 2. Microscopic evidence. The author emphasizes high-resolution microscopic studies of spent nuclear fuel, which reveal features such as spherical or quasi-spherical damage zones, radial microcracks and amorphous regions, patterns indicative of localized microexplosions or shock waves. These observations, according to the book, are difficult to explain by conventional models that only involve direct mass-to-energy conversion. 3. Implications beyond nuclear physics. Cosmology and astrophysics. The proposed fine matter could account for effects currently attributed to dark matter and dark energy, such as galaxy rotation curves and cosmic acceleration. Relativity. Phenomena like relativistic mass increase, length contraction, gravitational lensing, and even the precession of Mercury are re-explained in terms of interactions with this fine matter, not just space-time distortions. Wave-particle duality. The dynamics of this medium are also invoked to explain quantum behaviors seen in the double-slit experiment and particle diffraction. 4. Experimental predictions. The book lays out potential avenues for experimental verification, such as direct imaging and characterization of shockwave zones in irradiated materials, tracking the distribution and migration of fission products, astrophysical observations of cosmic phenomena with alternative expectations for fine matter effects, theoretical innovations. The book revives the concept of ether in a modernized and redefined context, proposing that a superfine, space-filling form of matter is produced in both terrestrial and cosmic events involving mass defect. This framework seeks to unify nuclear, quantum, and relativistic phenomena under a single, matter-based explanation, as opposed to the conventional split between mass-energy equivalence and space-time geometry. Paradigm shift. If validated, this hypothesis would not only alter nuclear physics, but also demand the re-evaluation of key tenets of special and general relativity, as well as quantum mechanics. The concept opens the door to new explanations for energy generation, space propulsion technologies, and a deeper understanding of the fabric of reality. Readership and style. The book is written to be accessible to both specialists and curious generalists. It balances rigorous scientific argument with visionary speculation, presenting its ideas in an engaging and sometimes provocative style. Readers are encouraged to question foundational assumptions in physics and consider bold alternatives backed by both experiment and logic. In summary, The Exploding Mass Defect is a catalyst for reimagining mass, energy, and the universe's inner workings, offering a coherent new paradigm that invites further exploration, debate, and experimental scrutiny. Core idea of the exploding mass defect hypothesis. The exploding mass defect hypothesis presents a fundamental challenge to conventional nuclear physics and the traditional interpretation of mass energy conversion. At its heart, the hypothesis proposes reinterpretation of mass defect. Instead of the missing mass in nuclear reactions being directly converted into pure energy, as described by Einstein's equation equals mc², the mass defect actually transforms into a new, extremely fine form of matter. Creation of fine matter. This superfine matter, which the hypothesis suggests permeates all of space, similar to the old ether concept, is generated explosively during nuclear reactions. Energy transfer mechanism. The rapid production of this fine matter is what imparts energy to the particles produced in nuclear reactions. The effect is likened to a tiny explosion, where the fragments are propelled by the expansive force of this newly created matter. Implications for physics. This reinterpretation affects how we explain nuclear processes, relativistic effects, and larger cosmic phenomena, suggesting that interactions with this fine matter underpin many fundamental forces and observations in the universe. In summary, the exploding mass defect hypothesis claims that the energy observed in nuclear reactions comes not from direct mass-to-energy conversion, but from the explosive creation of an all-pervading, superfine matter that delivers energy to reaction products and influences various physical phenomena. Microscopic evidence presented in the book. The book, The Exploding Mass Defect, Microscopic Evidence Rewriting Modern Physics, provides several forms of microscopic evidence to support its revolutionary hypothesis. Here's how the author substantiates the claims with experimental observations. 1. Electron microscopy of spent nuclear fuels. High-resolution imaging, transmission electron microscopy, TEM, and scanning electron microscopy, SEM, are used to examine nuclear materials after reactions. Observed patterns. These imaging techniques reportedly reveal distinctive microstructures, tiny cavities, shockwave patterns, and nanoscopic disruptions within the lattice of spent nuclear fuels. Interpretation. The author argues that these patterns resemble the aftermath of microscopic explosions, which cannot be fully explained by conventional theories of nuclear decay or fission. 2. Acoustic emission signatures. Detection of sound bursts. The book describes experiments